Imagine an automotive manufacturer asks three suppliers to develop software for one vehicle. Supplier A provides an exterior lighting function. Supplier B provides the network communication stack. Supplier C provides diagnostic software. A fourth company supplies the microcontroller and drivers. Every team is competent. Every module works correctly on its own. Then, integration begins. Supplier A calls a function named getVehicleSpeed. Supplier B provides readVehicleVelocity. One system expresses speed in kilometers per hour, another uses a scaled integer representing meters per second. One diagnostic module expects one fault reporting interface, while the application uses another. One microcontroller driver represents a channel with an integer, another uses a vendor-specific structure. Configuration information is stored in completely different formats. Nothing is necessarily wrong with any individual component. The problem is that the components do not share the same contracts. This is one of the fundamental reasons software standardization becomes necessary. As automotive electronics grew, engineers were no longer developing isolated controllers. Vehicle functions became distributed across many electronic control units, networks, suppliers, hardware platforms, and software teams. A change in one part of the system could create integration work across many others. Without common rules, every supplier can invent its own architecture, interfaces, naming, data representation, driver access, diagnostic concept, and configuration method. That creates several forms of dependency. The first is interface dependency. If one module expects a function called getSpeed with one data type, but another provides readVehicleVelocity using another representation, integration requires an adapter or software change. The second is hardware dependency. Imagine that the exterior lighting application directly accesses registers of one particular microcontroller. Moving the application to another ECU may require major rewriting even if the lighting logic itself has not changed. The third is supplier dependency. If application software depends heavily on proprietary services from one supplier, replacing one module with another supplier's implementation becomes difficult. The fourth is tool dependency. If every tool describes ECU configuration in an unrelated proprietary format, information cannot move cleanly through the development process. And the fifth is process dependency. When different organizations describe the same engineering work in fundamentally different ways, integration becomes a coordination problem as well as a software problem. Standardization does not mean making every ECU identical. It means agreeing on selected boundaries so independent teams can build components that can be integrated more predictably. Think about standardized shipping containers. Companies are free to put completely different products inside them. The standard does not specify whether the container carries electronics, food, or machine parts. It defines important external properties that allow ships, cranes, trucks, and ports to handle the container consistently. Automotive software standardization follows a similar idea. The application algorithm can remain unique, while selected interfaces, architecture rules, data descriptions, and infrastructure contracts become standardized. This distinction is central to understanding AUTOSAR. AUTOSAR does not normally tell a manufacturer exactly how its exterior lighting algorithm should decide when to switch a lamp on. That functional behavior can remain part of the manufacturer or supplier's competitive implementation. Instead, AUTOSAR focuses on areas where common rules create integration value. The first area is software architecture. In the AUTOSAR Classic platform, software is separated at a high level into application software, the runtime environment, and basic software. That separation helps prevent application logic from becoming unnecessarily tied to microcontroller-specific hardware details. The second area is interfaces. If software components exchange information through defined interfaces, the producer and consumer can agree on what information is exchanged without exposing every internal implementation detail. AUTOSAR even provides standardized application interface definitions for many established automotive domains. These focus on syntax and semantics of exchanged information, so reuse and exchange of software can become easier across projects. The third area is basic system functionality. Communication services, operating system concepts, diagnostic services, memory services, and hardware abstraction are examples of infrastructure that does not need to be reinvented with completely different concepts for every ECU project. The fourth area is machine-readable descriptions. AUTOSAR uses structured descriptions based on its templates and schema. These descriptions are commonly stored in ARXML files. An ARXML file is not software code. It describes system and software configuration information in a standardized form that engineering tools can exchange and process. This is important because modern automotive development is not performed inside one tool. System architects, software component developers, basic software configurators, network engineers, and integration teams may use different tools from different vendors. A standardized information model allows those tools to exchange engineering information more consistently. The fifth area is methodology. AUTOSAR defines relationships between engineering activities and work products. In other words, standardization is not only about APIs. It also provides a common framework for describing what information is created, consumed, and exchanged during system and ECU development. Now, return to the exterior lighting function. Without architectural separation, its application code might directly call a vendor-specific CAN driver, diagnostic library, non-volatile memory driver, and microcontroller interface. Move that function to new hardware, and much of the application may have to change. With a standardized architecture, the application can communicate through configured interfaces, while lower layers handle much of the hardware and protocol-specific work. That does not make migration automatic. The new ECU still requires configuration, integration, timing analysis, memory allocation, diagnostic configuration, network mapping, testing, and possibly adaptation. Standardization reduces unnecessary variation. It does not eliminate engineering. This is one of the most important misconceptions about AUTOSAR. AUTOSAR does not mean that any software component from any supplier can simply be copied into any ECU and work instantly. Compatible AUTOSAR releases, interface definitions, configuration, implementation choices, timing requirements, data types, safety assumptions, and integration constraints still matter. Standardization does not mean that every manufacturer must expose or standardize its competitive algorithms. AUTOSAR explicitly distinguishes standardized interfaces from the internal behavior of applications. The content exchanged between applications may be standardized even when the algorithm producing that content remains proprietary. This gives automotive companies an important balance. Standardize what benefits from industry-wide agreement while preserving innovation where differentiation matters. AUTOSAR began as an industry cooperation in 2003 because the growing software and electronic complexity was not a problem that one manufacturer or supplier could solve efficiently in isolation. Today, its standards span the classic platform, adaptive platform, foundation, and standardized application interfaces. The classic platform is particularly relevant to the deeply embedded ECU world we've been building toward in this course. If an interviewer asks why automotive software standardization is required, explain the integration problem first. Multiple manufacturers, suppliers, ECUs, hardware platforms, and tools must cooperate. If every participant invents incompatible interfaces and architectures, reuse and integration become expensive and fragile. Standardization provides common architectural boundaries, interfaces, data descriptions, and methodology so software can be integrated and reused more systematically, while application algorithms can remain differentiated. That's the real reason AUTOSAR matters. Subscribe to continue the course as we move from the problem that demanded standardization into the AUTOSAR framework itself. In the next lesson, we answer the obvious question created by everything we've just discussed. What exactly is AUTOSAR?